Hello, so this is lecture 4, where we're going to talk about the Fourier transform. Now lectures 4 and 5 will be about this topic, so we'll start introducing the Fourier transform today, and in the following lecture, lecture 5, we'll talk about the properties of the Fourier transform. Before we start, a little bit of feedback. Some of you have mentioned that the problem class last week was ruined really by the lag in the connection. So there was delays in some of your connections. And it was variable. So some people had very little delay and some people had really long delays that made it impossible to follow. So what I will do is I will try to slow down the pace. So I'll reduce the number of questions, I'll increase the time per question, and I'll try to slow down the pace so that the lag will have less effect. If you find it's impossible to follow, then what you can do is play these cahoots individually. What you won't get is the competitive nature of the game and my commentary, but you should still be able to follow the questions. So I find these cahoots really helpful because we start with some really easy questions and then they build up towards questions which are more similar to what you would expect in your problem sheets. So the general trajectory is we have really simple questions that we introduce at the Kahoot, and then that leads to your problem sheet questions, and then those lead on to the online tests, and those should prepare you for the final exam, or the whatever form the exam will take. And somewhere in between here you have your practice tests. So what we want to do is start from something that's very easy and build up so that you're ready for the exam when it comes. Okay, so on to our topic. So we're going to talk about the Fourier transform this week and next week. So we're going to look at this over 2 weeks, and you're going to have a class test covering both of these. So class test 3 will cover Fourier transform and properties of the Fourier transform. So where are we? This is week 4, and we're covering lecture 4. As I said, lectures 4 and 5, that's what's going into your next class test. Okay, so by the time you listen to this lecture, you will have already completed class test 2, and you'll have 2 weeks to prepare for the next class test. So, last week we introduced this idea of the Fourier series, and we said any periodic signal, any signal that repeats itself, can be represented using an infinite summation of sine waves. And we introduced this idea of a spectrum or a spectral plot. And we said these are just discrete lines representing the different components, and we call these components harmonics. And we said there's a fundamental, and then there's multiples of the fundamental, which are harmonics. And the amplitudes, so if you notice that there's an envelope there that governs the amplitudes. The amplitudes of these determines how good that is a representation of whatever signal we're trying to recreate. So if we're trying to reproduce a square wave, then the number of harmonics and the accuracy with which these amplitudes can be determined will determine how good that approximation is. We introduced this idea of distortion, this ripple. We refer to this as Gibbs phenomenon or Gibbs ripples. And we said that unless we have an infinite number of harmonics, which isn't possible, we'll always have some degree of distortion. So as you can see, the larger the number of harmonics, the closer the signal is to an ideal square wave. So we introduced this important expression there, and we said, importantly, that this combines the three terms, the DC term, the even components, and the odd components. The even components, I mean by that the coefficients of the cosine terms. And the odd components, the coefficients of the sine terms. So that's how you find the B terms. That's how you find the A terms. And A naught is just the DC term. It's just the average value. Now, if you notice, what's common in all of these expressions is this variable t. There has to be a period because this only applies to periodic signals. So all of this applies to periodic signals only. And that's important because today we're going to talk about the situation where your signal isn't periodic or isn't necessarily periodic. So we said that the A's and the B's can be combined into this compact form where you can find you can find C from A and B. We also said that the lowest frequency, other than the DC, will be something called the fundamental. And if you take multiples of the fundamental, that'll give you your frequency of your nth harmonic. So the second harmonic is twice the fundamental frequency. The third harmonic is 3 times the fundamental frequency, etc. So this is all a recap from lecture 3. So this is the Fourier series. Now this week we're going to talk about the Fourier transform. And that's for signals which are not necessarily periodic. So I said non-periodic signals, and I put non between brackets because it also applies to periodic signals, but it applies as well to non-periodic signals. So whereas a Fourier series had a discrete spectrum that looked like that, the Fourier transform might have a continuous spectrum. We're going to introduce the idea of Fourier pairs, and we'll quickly go over the idea of filters, low-pass filters, high-pass filters, band-pass filters. You'll come across this idea of filters in other subjects. I thought I'd introduce it to you here. Okay, so by the time you're listening to this lecture, you will most likely have already sat this test, and you'll be preparing yourself for problem sheet 4. So remember, when we speak about Fourier series, it's always about periodic signals, signals that repeat themselves. Okay, so this is a periodic signal with a period from here to here. So that's T. And if we have a signal that isn't periodic, how do we deal with it? We can't use periodic signals, sines and cosines, to represent a non-periodic signal. So what do we do? So remember this plot from last time? So this is our time domain representation, where you have a time axis going this way. And we said this is our spectral representation where you have a frequency axis going this way. And we said each of these spectral lines represents the amplitude of a sine wave. So here you can see each of these sine waves has an amplitude corresponding to the spectral line there. So the purpose of this is just to show you that a periodic signal in the time domain can be represented in the frequency domain. It just happens that we use the Fourier series to recreate or to create this spectrum. Today we're going to use something else to create the same spectrum. So bear with me, this is a strange visualization. If you're able to follow it, that's fine. If you're not, just ignore it. And that applies to 5 or 6 slides in today's lecture. So what we have is a frequency domain, or a frequency variable, and a time variable. So you have your red signal in time. So that is a time domain signal. And that is a frequency domain signal. So I'm going to use F, but they've used this symbol zeta. And what we're trying to show is that just like in the previous slide where we had a spectral representation and a time domain representation, these are the same. But notice that the frequency axis is no longer continuous. Sorry, it's no longer discrete, it's continuous. So let me show you again when it comes up. You see, it's sweeping across the frequency axis. All of these are continuous, no longer discrete. And if you add them all up, they should give you the time domain signal. So all of the frequency axis gives you all of the time axis. So what we're trying to say here is that the two signals are the same. They're just represented in 2 different domains. So the blue signal and the red signal, or the yellow signal in this case, are exactly the same. So for the Fourier series, what we had was a fundamental and then multiples of the fundamental. So these are what we call the harmonics. We added the harmonics together and we ended up with this signal. But this was periodic. If our signal isn't periodic, or isn't necessarily periodic, like this signal here, we also add sine waves together, but these aren't necessarily multiples of the fundamental. We don't have an F0 because we don't have a T. We don't have a T because it's not periodic. So here we're adding lots of sine waves together, but they're continuous. They're not discrete. Whereas here it's discrete. Here we have F0, twice F0, 3 times F0. Whereas here we don't have that discrete nature. So all of this is just to set the scene for the Fourier transform. Again, a little bit of an analogy. If you think of the colors that make up white light, again, you can think of it as being a continuous spectrum, and the frequency axis for a Fourier transform will be continuous. So this is a continuous variation of frequency. That's all I'm trying to say here. And again, this is all just trying to visualize for you, or to prepare you for what's to come. So what you're seeing here again is a discrete spectrum. By discrete, what do we mean? We just mean that these spectral lines are defined only at certain values of frequency. So the axis actually has an n And there you've got 0, 1, 2, 3. So this is a discrete axis. Why is the spectrum discrete? Because the signal is periodic. So with a periodic signal, we have a discrete spectrum. So just remember how that looks. Don't worry, you will never need to do anything like this or to represent anything like that. But it's good just to remember that these are two ways of looking at exactly the same thing, i.e. from the time direction or from the frequency direction. So here we have a function of time, and here we have a function of frequency, or a function of discrete frequency, n. But they're both the same signal. So this is just as much a square wave as this is. Okay. Remember, we introduced this idea of a envelope of a spectrum last week. So I said if I had a pulse train with a pulse with a particular width and a particular period, then this will give us spectral lines that have a particular shape, or the envelope of which has a particular shape. Now, it just happens, and you'll see this in the problem class, that this F0 is related to this period, and you know that. So F0 is 1 over t. We all know that. So F0 is 1 over t. We know that. What you might not have known is that the zero crossings here are related not to t, but to tau. They're related to the width of the pulse. Now, we're not going to change the width of the pulse. What we're going to do is we're going to make these pulses further and further apart. So we're going to increase t. So as t increases, F0 decreases. So these spectral lines become closer together. So become more closely spaced. Now, if this t becomes so big, it approaches infinity. We have a periodic waveform where the next pulse doesn't arrive until time approaches infinity. So it's as if, really, it's no longer a periodic waveform. It's just a single pulse. So what will happen to the frequency? What will happen to F0 if t approaches infinity? Well, F0 will become vanishingly small. It'll approach zero. So we'll have a situation where the spectral lines have become so close together, they become continuous. So that's where we say that a non-periodic waveform like this will have a spectrum which is continuous. That's when we stop calling it the Fourier series and we start calling it the Fourier transform. So that's where today's lecture starts, really. So, remember the Fourier series? Of course you do. We'd find AN, BN. And now what I'm going to do is I'm going to do a little bit of mathematics, but you don't need to worry about this, okay? So this is not important except to introduce the notation for the Fourier transform, which I'm about to show you. Okay, so if you just think of the A's and the B's being combined into a single complex variable, so something that looks like this. So you've got your A and your B, and that's your C, or let's call it 2C. Now, where am I going with this? Somehow I want to combine these two together. Oops, there. So now I can join these two together, and somehow using the Euler definition for or the Euler exponential expression, we can now represent f of t in a different domain, f of omega, where omega is frequency in radians per second. So now I've been able to convert f of t into something else, f of omega, by integrating not over one period, because this is no longer a periodic waveform. This is non-periodic, so we integrate over all time, f of t times e to the minus I omega t. E to the minus I omega t is simply cosine minus I sine. So this is the expression for the Fourier transform. It's really important. We'll be using it a lot. How we got here isn't really important, okay? I presented it because it's nice to know that Fourier series and Fourier transform aren't that different. One is very closely related to the other. But what we really, really need to know is this: how to use it, what to do with it, its different properties, which are coming up next week, and Fourier pairs, etc. So from this point onwards, it's quite important. Okay, so this expression again. Okay, so now we've introduced this new variable, omega, which is simply radial frequency. So we can write it, if anyone was in any doubt, omega is just a different way of saying frequency. So while frequency would be in hertz, f is in hertz, sorry, omega would be in radians per second. Okay. Other thing to note is that we use lowercase f and t for our time domain notation. We use uppercase f and omega for our frequency domain notation. And because our function is a function of time, we integrate over time. And as I said, there's no omega naught and no t because we're not dealing with a periodic waveform. Okay, so the important thing in this slide is this expression here. Now, for every transform, we need the inverse transform. The inverse transform allows us to recover our time domain expression from our frequency domain expression. So if we take our frequency domain expression, which is a function of frequency, and integrate it over all frequency multiplied by e to the I omega t, again, integrate over all frequency, this time not all time, that will give you, or divide by 2 pi because we're using omega rather than f, that will give you f of t. And that might remind you of the expression f of t for the Fourier series, where we had the same kind of thing, but instead of having integration, we had a summation. And the cosine and sine, that really is your e to the minus I, or e to the I omega t. Now notice another difference between the Fourier transform and the inverse Fourier transform is that here there's no negative sign in the power, whereas here there was a negative sign. So watch out for that. Okay, so we have a Fourier transform and the inverse Fourier transform. And just a little bit about notation. Remember I said a time domain expression is always lowercase. The frequency domain notation is the same letter but uppercase. And instead of T, we use F. Now, some textbooks instead of T, we use omega. Some textbooks might use F instead of omega. That's fine, but you'll notice that there's always a 2 pi factor in the expression as well. Some textbooks will use j omega. Some will use x of I omega. Okay, so there's lots of variation. For this module, I've chosen to use omega as the variable of choice. So if you're ever following an example from a textbook or from an online source, make sure you find something that matches the notation that we're using, or at least be aware that there's always going to be a factor of 2 pi if you're following a textbook that happens to use F. Okay? Now, another way to symbolize the Fourier transform is to use a curly F brackets x of t. So what that means is the Fourier transform of x of t. So the Fourier transform of x of t is x of omega. And the opposite of that is the inverse Fourier transform of x of omega is x of t. Another way of writing that is x of t, x of omega, they form a Fourier pair. Sometimes there's an F, sometimes there isn't. But it's understood that if there's this double-sided bracket between the lowercase and the uppercase, that indicates that these two are a Fourier pair. That means the Fourier transform of one is the other, and the inverse Fourier transform of the other is the former. Okay, so that's just a little bit about notation, the notation that we will use in this module. So, I said there's such a thing as a Fourier pair, where you have a time domain signal and a frequency domain signal. And an example of this is if you have a signal that looks like this, a triangular waveform. Now, it's not periodic, so it doesn't keep going. It's just a triangular waveform. Now, that will have a spectrum. And the spectrum happens to look like this. It's a Sinc squared. We'll look at a Sinc function in a minute. But that's the shape of the Fourier transform of a triangular waveform. Now, you don't need to know all the details of these. I expect you to know some Fourier pairs, and I'll make it clear which ones I expect you to know soon. In any case, your tests will be open book, but even when exams weren't open book, you're always given a table of the pairs that you might need. Okay, so if you have a good communications textbook, you'll have a table at the back generally, or in the appendix or somewhere. You'll have a table giving you these pairs. And in any exam I will give you the pairs that you need. So these are some more pairs. Some of them might be fairly obvious to you, some of them not so obvious. So a signal S of t will give you S of omega. That is just notation. But if you have some kind of pure sine wave, so a cosine in this case, in the frequency axis, you wouldn't expect it to have more than just that single impulse. Okay, so if we're assuming that this is the positive side of the frequency axis, you'd only expect it really to have a single frequency. So this is just a little example. A Sinc function will give you a boxcar function or a rectangular function. A Gaussian will give you a Gaussian, and a double exponential will give you something called a Lorentzian. Okay, all of these I can give you the mathematical expressions for them, but for now I'm just giving you an idea of how different signals look in the different domains. It's interesting to see that the Gaussian pulse, looks exactly the same. Okay, so Sinc function. We've seen the Sinc function a couple of times before, but we've never actually looked at any of its properties. So when we talk about Sinc function, different textbooks again and different websites will define it slightly differently. But basically a Sinc function is sine x divided by x, or sine t divided by t. Okay. So you might wonder what happens when t is 0. How come you get the 1? How is sine 0 over 0 1? Well, I'll leave you to think about that, but it's important to know that the zero crossings of a Sinc function occur at multiples of pi. Okay, so it's clearly an even function. Remember, the definition of an even function is where f of minus t equals f of t, and we can see that clearly here. Okay, and the amplitude decreases in inverse proportion to x. Now, even though we mention x here, what we mean is t. So even though this is all defined in terms of x, in our module, because we're dealing with signals, our horizontal variable or our independent variable, our horizontal axis, is always going to be t, time. Okay, why do we care so much about Sinc x? Again, this slide and the next few slides, not really important, but it's important for a few reasons. Mathematically, Sinc function and a rectangular function, they form a pair, and that is important. Sinc squared is the Fourier transform of a triangle function, and that's slightly less important. This just happens to be the case in physics, but really it's because it's very common. You'll see it a lot. So in 1 dimension or in 2 dimensions, or if you throw a stone in a pond and you look at the ripples, it's a very common function, and there are very good reasons why we need to understand its properties, and we use it a lot in 1 and 2 dimensional modeling in physics. So the Sinc function is something you'll come across a lot. Okay, so we will be looking at the Sinc function in 1 dimensions quite a lot. So whenever you see examples like this is really just for your information. You can happily just ignore this. Same here. If you're not interested, you can ignore this. But I'll say a few words about this, simply because I keep saying that an image is simply a 2-dimensional signal. So this is a 2-dimensional signal where you have, instead of having time, what you have is x and y. So this is a 2-dimensional image, and this is some images, because they're used extensively for comparison purposes. They're used to test, to validate, to compare algorithms for example, edge detection and compression. They become really well known. They're published a lot and republished. So, for example, this image of Lena comes from a 1972 Playboy magazine, and it was scanned 512 by 512 pixels and used extensively. So even today, people use this image quite a lot. So what we have here is a Fourier transform of Lena, but in 2 dimensions, because we have a 2-dimensional image. Is that really important for us? No, you can completely ignore this if you like, but it's really interesting. If you have an interest in image processing, if you ever end up doing any kind of pattern recognition, image processing, you will want to know how 2-dimensional images or 2-dimensional signals are processed. So it's interesting to see how this all relates. So these are a couple of videos I could play for you now, but they're included within the PowerPoint. If you're interested, just click on the YouTube links inside the PowerPoint. It's really interesting how they use this. They use the Fourier transform to actually do what they do in these videos, but I won't play them here. So let's spend a few minutes talking in some detail about what we're trying to achieve in this module. Okay, so I gave you a lot of introduction, a lot of context, a bit of visualization, a little bit of slightly irrelevant content about linear and 2-dimensional images. But now the stuff that really matters is how we actually deal with signals in 1 dimension. So here we have a 1-dimensional signal, a rectangular function or a rectangular pulse. Okay, sometimes we call this function a brick wall function. Because that's exactly what it looks like. Some textbooks will refer to it as a boxcar function. Some will just call it a rect function. But it is what you see, basically. It's a rectangular function. It is what you see. It goes up, across, and down. So it's like a brief pulse that lasts 1 second. So that's your function in the time domain. How does that look in the frequency domain? That's what we're trying to find. We want to know, what is the Fourier transform? What's the frequency domain representation of this rectangular function? So remember this expression that I kept showing you? We're going to use that. And all you need to do is replace f of t with its value. Its value is 1. Well, its value is either 0 or 1, depending on the range. So it's 1 between -half and half. And that's it. All you need to do now is integrate e to the minus I omega t. And if you put in the limits, -half to half, you end up with this. And with a little bit of manipulation, if you put a little 2 there and divide by 2, that'll allow you to invoke the Euler definition of sine and say, well, that looks awfully similar to that. And that allows us to say, well, that's just sine omega 2 divided by, sine omega over 2 divided by omega over 2, which is the same as sinc omega over 2. Remember, because sinc x is sine x over x. So we've managed to rewrite this to look like that. Did we have to do that? No, not really. We didn't have to. But if you'd stopped here, you would have no idea how it looked. It's just a strange expression with two exponentials and a complex variable in the denominator. Whereas this, we know what that looks like. It looks like a sinc function. It just happens to be a sinc function in frequency rather than in time. Now I said I'd say a few words about filters. There's a little video here. If it plays, it plays. If not, you'll have to play it yourself in the PowerPoint. But basically, we're trying to introduce systems that take a signal, and depending on the frequency of that signal, either allow the signal to pass or not to pass. So think of this as a response where the horizontal axis here is frequency. So this first kind of system, or this first kind of filter, is a filter which will allow signals to pass if they have low frequencies, but will block them if they have high frequencies. We call that kind of filter a low pass filter because it allows signals with low frequencies to pass. The opposite is something called a high pass filter because it'll allow frequencies with it'll allow signals with high frequencies to pass. So these signals will pass and low frequencies will not. A low pass filter will allow low frequencies to pass and high frequency signals will not pass. Notice we call these ideal filters because we have this perfectly crisp cutoff. We have a cutoff frequency that's perfect. It means that a signal is either below or above that cutoff frequency and is either allowed to pass completely or is blocked completely. In practice, signals or filters aren't perfect, and you would have seen that if you'd watched the little YouTube video in my link. But these are the ideal filter types. So low pass filter, high pass filter. We have something called a band pass filter, and that allows a pass band to pass. So between two frequencies, these are allowed to pass, but everything above that or below that are blocked. The opposite of that is called a notch filter or a band stop filter. It'll allow frequencies above a certain band to pass. It'll allow frequencies below that band to pass, but will block frequencies in between. So we have abbreviations for each of these. So this is a low pass filter. This is a high pass filter, HPF. Here we have a BPF, and here we have a band stop filter or a notch filter. And there are other types of filters, but I just wanted to introduce these because you'll often come across these in scenarios, situations, design exercises, or questions. So we're almost finished. Before ending the lecture, I want to leave you with a few things to do at home. So remember we spoke about convolution before? So we spoke about convolution in the time domain. This time, I want you to think about how convolution of two signals in the time domain, how does that look in the frequency domain? And the opposite. We'll think about if you were to multiply two signals in the time domain, how and why does that result in the convolution of the two spectra. Okay, so obviously I'm not going to assess this. It's not real homework. I'm not expecting you to upload it and share it with me. I expect you to do it because it's a worthwhile exercise. It's also a very common exam question. But we will be looking at this in next lecture. So in lecture 5, we will cover convolution. It's called the convolution theorem. But I won't be proving it. I'll be leaving the proof for you. And it's really easy to look up. You literally just have to put in the first few words of that into Google and it'll come up. Or any textbook will show you how to do it. But that won't necessarily be helpful in itself. If you actually spend some time trying to do the work, trying to take a signal, take two signals and convolve them, and then apply the Fourier transform definition and see if you manage to get that relationship. But we will cover this next week. So in summary, today, after a recap of the Fourier series, we introduced this expression here, which applies to periodic and non-periodic signals, and allows a signal in the time domain to be represented in the frequency domain. And we said the corresponding inverse transform is called the inverse Fourier transform. And it's a very similar integral. Let me just remind you of the key differences. We said that that minus sign is absent here. We're not integrating over time, we're integrating over frequency. We divide by 2 pi because we're using omega as our variable. And time here corresponds to a variable of integration t, and omega here corresponds to a variable of integration omega. And we said that whereas the Fourier series will have a discrete spectrum, the Fourier transform generally, unless it's a periodic signal, will have a continuous spectrum. We introduced the idea of Fourier pairs, and I gave you a few examples of this. And we introduced filters. So all of this was sort of to introduce you to what this is, how to use it, and what properties they have. All of this we'll be looking at next week. So, next week, this is what we'll be looking at. There is a problem sheet this week. It'll cover everything we've covered. Next week, the problem sheet will be more substantial because it'll cover 2 weeks' worth, and then there's going to be a class test. That's likely to be the hardest class test because it's actually the hardest topic for Fourier series, Fourier transform. Everything after week 5 is really downhill from Fourier transform. So if you're still following, if this is still making sense, then you should be okay for the rest of the semester. Okay, so that's the end of today's lecture. I hope you found it helpful. I hope you all do well or did well in the second class test. And good luck with your revision, and I look forward to seeing you all on Monday.